Hi everyone, and thank you all for joining us today. My name's Tom Pritchard, and this is the fourth in our series of LimitState webinars for 2016. Your presenter for today's session is Dr. Colin Smith, who is the LimitState GEO Product Manager, and he's going to demonstrate how you can undertake more informed slope stability analyses using LimitState GEO, which is our geotechnical analysis software. The main section of the webinar will run until approximately 10 past 1 UK time and should include about 5 minutes at the end for questions if you have any. And you can post these at any time during the webinar using the question panel that should be present in the webinar interface in front of you. And we'll try and answer as many questions as we can during the time available, but obviously given the short amount of time this isn't always possible, and we do apologise in advance if we can't get round to yours, but we will follow up on any questions that we get sent after the webinar is finished. So our speaker for today, as I said, is Dr. Colin Smith, and I'll now pass you over to him.
Thank you, Tom. Well, good afternoon to those of you in the European time zone. Afternoon or evening to those of you joining us from elsewhere in the world. As Thomas mentioned, my aim today is to show you how you can get more from your slope stability analysis with LimitState GEO. So to this end, I'll primarily be using the software directly to illustrate key points, but I'll make use of a few slides at the beginning and at the end for an introduction and summary. In particular, we'll be looking at two specific issues: capturing non-standard slope failure modes and carrying out what-if type analyses, and that second one will include a look at adding other geotechnical features into problems. I think it's useful first to give you a little bit of context about the software and to the company LimitState. The University of Sheffield has been conducting research into limit-state analysis and design and use of optimization in civil engineering for almost 2 decades now. LimitState itself was spun out from the University of Sheffield in 2006 with the aim of making this research available to industry, providing easy-to-use and powerful software tools that are well validated and supported. Now, the company has 3 products at present: LimitState Ring, LimitState GEO, and LimitState Slab, with several more in the pipeline. And these are used by a wide range of consultants and contractors, large and small, in over 30 countries worldwide. Now, if you've used the software before, LimitState GEO is a general-purpose ultimate limit state software, able to determine the collapse state for any problem geometry and able to model slopes, retaining walls, structural elements, and soil reinforcement as shown in some of these examples. Our aim today is to focus on slope stability analysis. Now, I'll just take a brief overview. If we examine standard textbooks, we'll see a number of conventional analysis methods suitable for hand-type calculations. We'll just look quickly at 3. So the simplest is probably planar slip analysis, really only applicable to infinite slopes, but it's straightforward. And by looking at simple equilibrium, we can determine a factor of safety, which in this case is effectively determined as a factor on soil strength. Slightly more sophisticated, perhaps, is a Taylor slope stability analysis. This is focused on undrained slopes, assumes circular slip surface, and Taylor looked at a whole range of different slip surfaces and found the optimal one that was most critical for collapse. But again, the output from that is essentially a factor of safety determined as a factor on soil strength. Perhaps more complex still is the method of slices. In this approach, which is a limit equilibrium approach, assumptions are made about the slip surface shape. Typically, they're assumed to be circular, and where it's located. The mechanism doesn't necessarily have to be kinematically compatible, and because the problem is not statically determinate, we have to make assumptions about interslice forces. But it's not required that the slices are necessarily sliding relative to each other. So that adds a few assumptions to the analysis, but generally it's found to give good answers across a wide range of problems. And again, when you carry out this type of analysis, the factor of safety that you'll get out can be defined in terms of a factor on soil strength. So this is probably the most popular general purpose slope stability analysis method. It was developed primarily to facilitate hand analysis, but of course it's much easier when it's been automated. And this is one type of geotechnical software that you will find. Now, just taking an overview of geotechnical analysis software, if we survey what's available, on the one hand, up in the top left-hand corner, we have those that are kind of based on conventional approaches, such as a method of slices, and they do a pretty good job, specifically for slope problems. At the other end of the scale, on the bottom right of the screen, we could be using complex finite element analysis, which can model any problem geometry and complex soil behavior, but typically requires a lot more time and expertise to use. What we feel filling the gap in the middle is computational limit analysis, which provides the geometrical flexibility of finite elements with the easy use and simplicity of traditional methods. Essentially, it's ultimate limit state analysis. The only parameters you need are cohesion, friction, and unit weight, but it can solve any geometry that you like. And such methods can be applied to geotechnics, but also looking at the software that LimitState has available to masonry arch bridge analysis and to the analysis of concrete slabs. Now, all these methods are based on limit analysis. This is a form of analysis that assumes a rigid plastic behavior of a material. So it's an idealization, but it's commonly used, has been used for decades in geotechnics. And the very nice thing about it is that you get what are called the upper and lower bound theorems that allow you to determine the true plastic collapse load. So these are rigorous plasticity solutions. If you adopt what's called a limit equilibrium approach, then some of these conditions are relaxed somewhat. Now, a LimitState GEO software, which we'll be looking at in a moment, essentially employs an upper bound method using an approach called discontinuity layout optimization. No additional assumptions are required. You just click the button and solve, essentially. And it can determine a factor of strength applied to the whole soil domain. And what the software does is automatically determine a critical failure mechanism. So just briefly run over how this method works. It uses, as I said, a technique called discontinuity layout optimization. It's a rapid and direct means of analyzing the collapse state. It was the outcome of a 5-year EPSRC funded research project. And the key method was published in 2007 in the Proceedings of the Royal Society. Basically, what this approach does is convert that geotechnical collapse problem into a simple linear optimization problem. And I can describe in 4 diagrams the essence of how this works. So here we have a very simple problem of a rectangular block of soil with a load on the top and supports to the left and the bottom. Instead of populating the populating the domain with elements, as in the finite element method, we populate the domain with nodes. Here, we've just got 4 by 3 nodes, that's 12 nodes. And what we do essentially is we connect every node to every other node with a potential slip line. So in this case, we would have 12 times 11 over 2, 66 possible slip lines. That is then converted into a linear optimization problem, and the optimizer will pick out from that set of 66 slip lines the critical, I think, 6 slip lines here that form the collapse mechanism that dissipates the least energy. So that's the critical collapse mechanism, and the software will normally run with 500, 1,000, 2,000 nodes, looking at millions of potential slip lines, and so it's able to get very, very close to the true answer by optimizing all those possible failure mechanisms. Once it's solved, so this example, we've got a slope stability problem. the software automatically ties together all those slip lines and animates them to allow you to assist with interpretation. And a key point here is that the accuracy of the result that you get out is dependent on the starting number of nodes, because that determines the set of potential slip lines that it can try and select the critical mechanism from. So the more nodes you use, the more accurate the result, but of course it will take a little longer to solve. Now, clearly, if you've not come across this method before, you might be wondering, does it actually work? Is it accurate? Well, we've calibrated it against many solutions in literature, and we get almost always very close matches to the loads. A lot of these results are available on the website. You can download them. You can see the benchmark result from the literature, the result from the software, and the discrepancy. So this example is a slope, and it's 2% out from the benchmark result, and you can actually download the file and test it out yourself. We can also do comparisons with, for example, Taylor stability charts. So here's just a small look at two types of slope failures, and again the software gets very close to the Taylor results. And an increasing number of papers are being published using this method. You can download a bibliography from our website. Here I've just highlighted a few papers looking at slopes and embankments. So that's the introduction. What we're going to do is now actually use the software and look at how to use that to solve a whole range of problems. First of all, we're going to focus on non-standard failure modes. So I'll just start the software. So when the software starts, this is a standard layout. You see a number of buttons along down the left-hand side, along the top, and various sub-windows. So I'll explain these as we go along. If we want to solve a problem, I can click this button, which is create a new project. If I want, I can click empty and draw my own geometry for whatever problem I want to solve. But the software comes with quick build wizards to create standard geometries, which can then be modified later on. So we're focusing on slope stability here, so I'll just work with that one. We can put some general data about the problem in, which I'll omit. This wizard allows you to define the geometry, slope height, width, etc. I will just stick with the defaults here. We can put in a water table as well. I'll stick with the defaults, and the soil type. So here we can enter soil properties, undrained shear strength, unit weights, and drain properties, depending on the soil type that we wish to work with. Here I'll stick with the defaults, so we're going for a clay for an undrained strength of 50 kPa, unit weight of 20. We could apply a surcharge if we wish. I'll leave that at 0. And the software comes fully enabled to apply Eurocode or any partial factors that you like. Primarily designed for Eurocode, but it'll be easier to adapt to other types of design codes, and it allows you to apply factors as you wish. In this case, we're just going to work with unit factors everywhere, so effectively we're not applying partial factors. And we're going to adopt what's called a factor strength analysis. So we're going to get the software to tell us what the factor of safety on strength is, essentially from this result. We can also get it to do a factor load analysis, but for slope stability, we're primarily interested in factor strength. This last setting here is the nodal density. So if you recall, I said the more nodes we put in, the more accurate the result. What I'm going to do is just set that to coarse. So that's only using 250 nodes, which is still generally enough for most slope stability problems, and that's really just primarily for speed, so that we can run through this webinar fairly briskly. So I click finish, and it draws a problem there. And essentially, this is an undrained slope problem, very steep slope, of the type solved by Taylor. So we're in factor strength mode. So all I need to do to solve it is click the solve button up here. And rapidly it iterates to the collapse mode. And you can see the animation. Now that animation is taken past the kind of limits of validity of the solution. That's purely for illustrative purposes. So when you start seeing sharp corners sticking out here, that's simply because the animation is strictly only valid at the instant of collapse. Now, result here, the terminology we use is adequacy factor, but we can interpret that as a factor on strength. And that basically means the result that we get out here says that for this system to collapse, the soil strength has to be 2.477 times less than it currently is. Now, anything I click on in this problem, its properties appear in a property editor here on the right. So if I click on the main mass of soil, it's called a solid, and I get various properties, and I can see in it we've got a material called soil A. If I click there, this is a soil we defined, had an undrained strength of 50. Now we're told that if we reduce that by a factor of 2.47, the system will collapse. So I'll just divide that by 2.5, so I'll stick a strength of 20 in, and I reanalyze the problem, and you can see that we get a factor pretty close to 1 here. As we would expect, we're right on the point of collapse. Now I can also access soil here in the Materials Explorer here. I have a whole range of materials that I can use. So soil A here, I'll just going to revert that back to 50. And if I modify the slope angle, you see that I can get a different mechanism. So I'm going to make this 6.25. So just push the angle back a bit. And if you're familiar with Taylor's analysis, as the angle gets shallower, then we get a failure that doesn't go through the toe. It actually comes under the toe. That again is reflected in the software analysis. Now, strictly, this analysis isn't valid because the mechanism, if you look up here at the top right-hand side, intersects this boundary. Now, this is an artificial boundary just to keep the domain of soil finite. I could move that out to the left, and so I should always check that. The problem with this particular analysis is that, in fact, the mechanism gets out to be of infinite size, essentially. So no matter how far I move the boundaries, the mechanism just keeps following it. But that's what we expect. That's what theory actually tells us. Now, as I said, we use the coarse grid for speed just at the moment, and this is the kind of set of nodes that we get. So we'd still get a pretty rich set of potential discontinuities. If I say medium there, preview the nodes, then we get a higher density, and we'd get a slightly more precise result. But it's only gone down by about 0.04, I think, in that case. Anyway, I shall revert back to course. So that's the basics of the software. What I'll do is just use this example to illustrate a kind of non-circular or unusual slip modes. So what I'm doing here is I'm using the drawing tools on the left to add in a line to the problem. And actually I'll make that, oops, a little bit thicker. I'm going to put a very soft clay down there. So in this particular case, the slope failure mode changes, and effectively we start squeezing the soil here. It's not. I'm going to actually go to the medium nodal density, but effectively we've got a kind of slope failure here and squeezing of soil here. So the slip line is not just going through here, but we're actually getting slippage and extrusion. So that would be something that would be very tricky to capture with just a simple slip circle or method of slices type analysis. Now I could use the software to illustrate some other sort of non-circular, non-standard failures, but as we're trying to keep this webinar quite short, I will revert back to the slides and just show you a few examples. So here's another model that we've run. So this is on layered strata with a retaining wall and a water table. What you can see at the top right is that the slip surface dives down to basically a weak interface between the two strata. But as it gets closer to where this retaining wall is, then the slip surfaces have to dive under that and then come up underneath. So again, highly non-circular, but the software will capture all of those failure modes, just seeks out the most critical mechanism. And one slide here. So related to slope stability problem is an embankment. So this is a failure of a reinforcement embankment over a soft soil. These images are actually from a paper that's just come out in Geotextiles and Geomembranes, looking at analysis of a reinforced embankment over soft soil. So you can get a whole range of failures. If the underlying soil is quite strong, then the embankment itself will fail. If the underlying soil is quite soft, then you get a deep-seated failure. However, if the upper layer is quite strong and the reinforcement is quite strong, then effectively you start extruding the soil, the soft soil underneath. And a final failure mode is where you get that type of extrusion, but actually instead of the whole embankment sinking vertically, it actually rotates, the shoulders rotate sideways, and you get a sort of combined rotation and extrusion. So again, the software is able to capture these complex failure modes, which would be very hard to pick out with, for example, a slip circle or method of slices approach. So that's looking at different failure mechanisms. The other advantage of the software that a lot of users find very valuable is the speed at which you can do what-if type analysis. Now, you've already seen me modify the geometry a little bit in the previous problem. We'll just look at that and all the a whole range of features that we can in fact add. So we're going to look at a very simple core problem, which is a slope 10 meters high, 20 meters long, on a soil of a C-5, phi-30, and a unit weight of 20. If you do a method of slices, Bishop's simplified method, you get a factor of strength of 1.6 for this problem. But that method requires you to assume what the nature of the interslice forces are. And typically you're going to have to specify zones of entry, exit points, centers of rotation. With LimitState GEO, that is not necessary. You just we assume the principles of plasticity, and the software will identify the critical mechanism. So I will bring up that model, which I think I have pre-prepared. So this is the problem. If I click solve, well, we'll just check. So this soil is called soil A, and you can see it has C-5, phi-30, unit weight of 20. So I click solve. Software iterates a little bit to get to the optimal solution for that factor of safety, and we get a result of 1.63 or 1.64. So that's very close to that from the method of slices. And of course, the method of slices being limit equilibrium has no formal status, whereas this is essentially a very accurate upper bound plasticity solution. Now, that's analyzing essentially a dry slope. We could say what happens if we get a lot of water in there. I haven't got time to describe all the possible water pressure modes, but the simplest is just to draw in a phreatic surface. So we could say there's a phreatic surface coming in here, like so, and I can solve the problem again. And what we should find, as we expect, if we add water to a slope, then clearly the stability is going to go down. And let's take it, give it a little chance. Yep, so it's pretty well got there now. The factor adequacy on strength or factor on strength is 1.47, so it's come down a little bit from 1.63. I will just clear the water table, so we don't have too many features in at once. Now, it may be that you're analyzing this slope, but there's concern that there was a pre-existing slip surface in there. So you can quite easily add those. So I'm just going to add a very simple one, fairly planar, but I'll just make it slightly curved, and Just for simplicity, I'm going to put a very weak material on that. I'm going to assume that that is a pre-existing slip surface that has the strength of a very soft clay. Fortunately, that colour that material is almost the same as the original material, so you can't quite see it. But if I click Solve, what you'll see is that the software seeks out a mechanism that uses that weak surface, as you'd expect, and doesn't go fully to the toe of the slope. And we have an adequacy on strength, or factor of safety on strength, of 1.22, so that's come down from 1.6. So as we expect, that has reduced the strength of the material. So this button up here is an undo button, so I can undo those changes and remove that addition. So you've got this slope, and maybe someone says, well, what happens if we put a load in the middle of the slope? So let's do that. So I'm going to add a couple of points on the slope here. Just trying to get them to around about the So supposing I put a little bench in there, and I'll use this polygon draw tool. I'm going to draw in a kind of little foundation, and I'll make that out of concrete. And I'm going to put a load on that, so I'm going to put a load, a permanent load of say 40. So that's a pressure of 40 kPa on that. So I want to see what that does to the analysis, so click Solve. Now, what I've done, of course, is I've got a vertical cut in a soil which is mostly frictional, a little bit of cohesion, so the software just identifies that that is clearly going to fail. So that ain't going to work. But what I can do is I could just regrade the upper slope a little bit and just pull that down to there. So let us see if that helps out a bit. So software looks at the whole range of different failure modes and tells me that that upper slope is going to fail first rather than the lower slope. So this weight is not big enough to cause the lower slope to fail. And we can see the upper slope is just slightly steeper. However, if this load becomes too big, so I will set it to say 200, and then we analyze. Then the software says, that load's now too big, with the lower slope is actually going to fail. So that's where our critical mechanism is. So it will certainly seek out the critical failure mode. Now, I'll just remove that slope, so we'll just undo, get that back to where we were. And just reanalyze it, so we'll just go back to that 1.66 result, or 63 rather. Now that's probably strong enough, but if we wanted to increase the stability, one way of doing that is to add a berm at the base of the slope. So I can again use this polygon tool and draw in a block of soil along the base. I'll use a dense sand as a fill on that and reanalyze the problem, see what that does, see whether that actually improves the stability. And in this case, it's had a small effect. We've gone from 1.63 to 1.77 on the factor on strength, and the mechanism has been moved upwards, so it doesn't want to go through this dense sand. Now, while I'm got that solved, I'll just show you that once you've got analysis, you can generate a report. So click on a report here, and gives you a little bit of background of the information that you put in, the type of analysis, the failure mechanism that you've got, details of all the geometry, materials that you've used, material properties, and so on. And you can switch those in and out as you like. And this comes out as an editable file, so it's very easy to import into, for example, Word and edit that. Now, you may decide that this berm is not the right solution, and that actually perhaps it would be better to try and maybe a sheet pile wall or some piling. So we can look at what might happen, just to keep it simple. If we put some sheet pile walling down the middle of the slope, so just draw a almost vertical line there, put in a base there. Now, it's very easy to add elements such as sheet pile walls or geotextiles or soil nails. They're defined as what's called engineered elements. I haven't got time to sort of go into those in great detail, but we have some predefined materials here. This is a sheet pile wall that's rigid, and I could just drag and drop that material across, land it on that line, and this line is now represents a sheet pile wall. And if I click solve, you can see that it's trying a few mechanisms, but the mechanism that it's going to land up on, essentially it's expanded the size of the failure mode, and to fail it's going to have to rotate that rigid wall sideways, and our factor of safety on strength goes up from about 1.63 to about 1.96, so that's a bigger improvement than using the berm. And it might be that we want to do that in order to have access to the land below that level. So if I want to check that out, I could delete that, see if that wall has got enough capacity in it to support the slope above it, so I can cut away into the toe of the slope. And you can see that now the factor of strength has dropped from 1.63, well, or 1.97 as it was before, down to 1.3. So it's still above 1. So it's still a pretty decent margin of safety, but clearly lower than if we hadn't removed that material. Now, if I undo those features, I may say, well, I don't want to put sheet piling in there. Maybe I want to try some soil nailing. So again, we can install that. So soil nailing will normally go in at a raking angle, and I'll just, for the purposes of illustration, put in one soil nail. Now I've got a predefined soil nail here. What I'm going to do is duplicate that material. So I click duplicate. I get a copy of it up here. The reason I want to do that is I want to amend the properties. Now again, I haven't got time to go into the details of modeling this, but essentially I have to put in the right pull-out factors that correspond to the soil type that this nail is in. So I'm going to put in a pull-out factor. The cohesive component of that is 2, and the frictional component is 0.2. We can model lateral factors, and that basically models the resistance to lateral movement. Normally that's ignored in conventional analyses, so I'm going to set that to a very low value, and I'll leave the other values fixed. So basically we're modeling a rigid nail, and again I can drag and drop that onto here, and I've now got one single soil nail in this problem. And essentially I'm modeling this one-dimensional soil nail in this two-dimensional software, but it's modeled. Its properties are presented averaged out per unit width into the diagram. Again, and I click solve again. So the failure mechanism you can see here, unlike with a sheet pile wall, is able to go through the soil nail, but the soil nail will still contribute some resistance through tension, the tensile and shear forces between the nail and the surrounding soil. And that one single nail hasn't had a huge effect, but it's increased the factor of safety on strength from 1.63 to 1.73 in this case. And the software actually plots out, this is a graph of the axial force along the nail. So you can see it obviously drops to 0 at each end and builds up. So if I added more nails in, I could get that factor of safety up further to whatever level I wished to take it. So I hope that's given you a flavour of the sort of what-if type calculations and modelling that we can do. Very interactive, try out things, get a feel for the problem, and can incorporate a number of elements such as sheet piles, soil reinforcement, etc. So we'll quickly jump back to the PowerPoint at this point and wrap up. So what I hope you've seen from this short presentation is that using the software, it's as straightforward as a conventional method of slices in terms of the parameters that you need to feed in. However, it's simpler in that you don't need to specify entry-exit points. You don't need to choose solution method. Is it Bishop? Is it Jambu? Whatever. You don't need to worry about interslice forces or a search space. The software will simply seek out the most critical mechanism, even if it's highly non-circular. And again, I hope you've seen that the workflow is straightforward from geometry import to reporting. So the user interface very much puts you in control. You can solve the problem with one mouse click. And while we didn't look at it in detail, handling partial factor application is as simple as choosing the right partial factor set that you want to use. Hopefully, again, you've seen the interactivity and how we can use this software to look at what-if type questions. So it empowers you to get a much better feel for the problem and to explore what might be the best solution. And of course, the software is not just limited to slope stability. You can solve any ultimate limit state problem type, whether it's a foundation problem or a retaining wall problem, etc. And there's no need to impose any idealizations or corrective factors for non-standard geometries. You can put in any geometry you like, and the software will solve that. So that brings me to the end of this presentation. I hope you found that useful and informative, and I'm happy to take any questions at this stage. Okay, so first question is, can this presentation be accessed? So, yep, we'll put the presentation, a copy of that up on the website, so you can download that again and refer to it. Okay, so I've got a question on how does the program output the moment and shear demand on shear piles. So if you're putting in a pile into the ground in order to reinforce the slope, for example, essentially you have to model it or represent it using the same model as a soil nail, if I've interpreted the question correctly. So basically the software works out how much you have to enter a value, the failure load at which the soil will effectively flow around a pile, and the software will take account of that in its global analysis and be able to apply that appropriately in the analysis. Knowing that and knowing where the mechanism is, it's then able to work out the pressure distribution on the pile and thus infer the shear forces and the bending moments in that case, and that's what you see plotted in the problem. Okay. The question, is there a training support package to accompany the software? If you buy a copy of the software, you automatically get a 1-hour webinar to guide you to initial usage, and that can be tailored to specific problems that you like. If you wish further training, that can be arranged, and we're very happy to arrange that if you just contact the support at LimitState to discuss your needs. That can be arranged. Got a question: can you vary the nodal density within the soil to focus on a failure mode? So yes, we can do that. So for example, if I just bring up an example of a, where is it, stem wall, okay. So this is modeling a concrete stem wall. Now, if I analysis preview nodes, what you can see, probably the color's not very helpful here. I'm just going to change this color to something slightly less. So you can actually see that we've got the software by default has put more nodes in the basal region here. It's quite easy to edit that. So if I click on here, we've got a local spacing of 1/2 and 1/2, whereas in this zone we've got a local spacing of 1 and 1. So if I want even more nodes down here, I can put in, oops, I can put 1/4 and 1/4 in. And you see I get even more nodes there. And that's just to help the software. In this particular case, because we're underneath the foundation, we might get a squeezing failure. The software puts that in. Now, when I've solved it here, it's actually just sliding on the interface, but if I make that soil a very soft clay, I should be able to induce a nice squeezing failure. And then that's when it's useful to have a lot more nodes because the mechanism gets quite complicated. So normally you can see from initial solutions where the mechanism may be getting quite complicated, then you can tailor the nodes to that position. And so that means you get an efficient analysis rather than putting nodes sort of out here on the far right when they're not really needed, and that then just eats up computational time. Let me go through the questions. So just another question relating to bending moment and shear force diagrams for sheet pile walls. They can be plotted on the screen. So let me just bring up sheet pile wall model, and I'm going to put a sand in there. So this is a sheet pile wall embedded in clay. It's a short-term analysis, but it's got sand behind it. So the wall is falling over there. So here we're plotting the actual bending moment, and you can scan down and see the values of that. I can right-click on there if I wanted to see the tensile force, which is kind of meaningless for a retaining wall. In fact, it doesn't pop up at all. I could do that. I'll reverse the moment. And what you can do is you can export those into a spreadsheet. So if you want to actually get the values and look at those, then you can export them. And as long as the failure mode encompasses that part of the wall, those are going to be the actual failure collapse state. Normally it'd be best to do these using factor strength mode rather than a factor load mode. But if you have a look at the manual, it explains the details of getting those values out. So another question relating to piles. So piles in clays or large diameter piles, yeah, in clays. Effectively, as I've just said, you can represent those using the soil air model, but it's up to you to decide that that's the right idealization, and you have to enter the force required for soil to flow around a pile. So, for example, a pile in a clay, typically to get soil to flow around it as a failure mechanism, it's around about 9 or 10 cu times the diameter of the pile. And you can enter that value into the software, and then that will, if the software models the soil flowing past the pile, it will impose that force on the pile. So the software is able to pick the right size of mechanism, taking those factors into account. So that allows you to model that pile area. Okay. So I think with the answer to that question, we are now out of time, onto our 45 minutes. So I will pass back to my colleague just to wrap up. Thank you very much for listening. Over to you, Tom.
Thanks, Colin, and thanks everybody for taking the time to join us today. As Colin said, we've now reached the end of the webinar, and we do hope you found it informative. And for people who are current users of the software, then obviously we hope you learned something new about it that maybe you didn't know before. And if the webinar has prompted any questions about it, then please do get in touch via telephone, or you can email us on info@LimitState.com, and we'll be more than happy to help out. For people who aren't current users of the software, we'll be in touch over the next few days just to get some feedback from you, find out if you have any further questions about LimitState GEO, especially with its application to slopes, and see if it's a useful bit of software for you. If you'd like to watch the webinar again, I know we had a question about that, then we will post up a link to that. It will either go out to later today or early tomorrow morning, and you can share that freely amongst your colleagues if they may be interested to see it as well. Finally, everyone might be interested to know that there's going to be a number of other scheduled webinars that deal with LimitState GEO and its application to other problems. So please look out for the event notifications that will be sent out via email and also posted on our website at www.limitState.com/events. Finally, I'd just like to say thank you again for listening, and hope that you can join us for one of those future sessions. Goodbye.